Well, welcome back. We are going to talk today about indirect proof. And I'm going to show you how to do indirect proofs by using um, maybe some games that you're familiar with. A lot of times you may have seen Sudoku games, and I know I've given those to you in the past. And here's a little game where the goal of this game is to fill in the empty squares where you have the numbers 1 through 4 appearing in every row and every column. So it's just like a Sudoku, only a little bit smaller. And the way that you do some of these is to go ahead and use what's called indirect reasoning. And indirect reasoning, actually what you're doing is you're considering all your possibilities, but then you prove that one of them's false, which leads you to conclude that the opposite one or the only one remaining has to be true. For example, if I take a look at this row in yellow here, we already have a 1 and a 2, so our possibilities that remain are 3 and 4. Well, if I look at this first box here, this cannot be a 4 because there's already a 4 in that column, so it has to be a 3. So what I've just done is I've used indirect reasoning. It cannot be a 4, therefore it must be a 3. And so that kind of reasoning is what we use to use what's called indirect proofs. Okay, so here is your process for doing indirect proofs. The first step you're going to do is you're going to assume the opposite of what you want to prove. And then once you make that assumption, you're going to show that it leads to a contradiction. That's your second step. And your third step will be to go ahead and conclude that the assumption you made is false, and so therefore what you want to prove is true. So it's kind of a backwards way of proving things. So let's take a look at how we're going to write our very first step. So the first step of writing your indirect proof is making that assumption of the opposite of what you want to prove. So here's just a couple of statements, A and B, that I want you to see if you can figure out what your assumption should be. So just for the first step, we're not going to do the actual proof, but just set up that first step. So the first one says you do not have soccer practice today. What would be the opposite of that? And the opposite would be to take out the word not. So the opposite statement would be you have soccer practice today. How about letter B? An integer n is divisible by 5. Well, oftentimes we can just insert the word not to get the opposite. So this one would be an integer n is not divisible by 5. That would be your assumption. Assume that it's not divisible by 5. Here's a chance for you to try a couple of them on your own. Go ahead and pause the video, try to work on A and B and come up with your statements, and I'll give you some solutions when you get back. All right, I hope you had a chance to take a look at those. Letter A says at least one pair of shoes that you bought cost more than $25. Well, one of the assumptions, this is not the only assumption, but one of the assumptions you could make is that none of your shoes cost more than $25. That would be the opposite of at least one pair cost more. Letter B is triangle BOX is not acute. Well, we could just take out the word not and say triangle BOX is acute. We could assume that and then proceed with our proof. All right, so in problem number 2, we're going to look at which of these three statements contradict each other. So statement 1 says segment FG is parallel to segment KL, congruent to segment KL, equal in length, and statement 3 says segment FG is perpendicular to segment KL. Well, let's compare the first two. Could we have two segments that are parallel and the same length? And yes, we could. That could actually happen. They can be the same length and still be parallel, so they don't contradict each other. What about 2 and 3? Could we have segments that are equal in length and be perpendicular to each other? And that can also happen. So those two are not a contradiction. Well, our last two to compare is 1 and 3. Can we have two segments that are parallel and at the same time be perpendicular? Well, no, they can't. So there's our contradiction. We can't have segments that are parallel and perpendicular because parallel means they don't intersect and perpendicular means they do. So our contradiction is in statement 1 and 3. Here's a chance for you to try. Go ahead and pause the video again. Here's 3 statements. See if you can figure out what the contradiction is. So you might have to look up what the definition is of acute, scalene, and equiangular. And actually, let me just go ahead and give you those here. Pause the video and see if you can figure out which ones of those statements are contradictions. All right, hope you gave that a try. number 1 says triangle XYZ is acute, which means all the angles are less than 90 degrees. Can we have an acute triangle that's also scalene? Scalene says all the sides have different lengths, and that could be true. We could have a triangle that has all different lengths of their sides and all the angles are still less than 90. That could happen. What about acute and equiangular? Could we have all the angles less than 90 degrees and have them all be congruent? And that can also happen as well. We could have an equilateral triangle where all the angles are 60 degrees. So equilateral triangles are also equiangular and they're also acute. So the contradiction is between 2 and 3. We can't have all the sides being different lengths and all the angles being congruent, because if all the angles are congruent, then their side lengths will be the same as well. So 2 and 3 are our contradictions. So to write an indirect proof, here's problem number 3. We're given that triangle ABC is scalene. Remember, scalene means all of the sides have different lengths. We want to prove that all 3 angles have different measures. So we're going to assume temporarily the opposite of what we want to prove. So if we want to prove that they all have different measures, all the angles, we're going to go ahead and assume that 2 of them have the same measure. What if we assumed that A and B were equal in measure? That's how we're going to start our proof. So if A and B are equal in measure, then we had a theorem for isosceles triangles that said if 2 angles are congruent, then the sides opposite those are also equal in length. That was called the converse of the isosceles triangle theorem. So that means that 2 of the side lengths of the triangle would be equal in measure. Well, that already contradicts what it means to be scalene. Scalene means that all 3 sides have different lengths. So we've already found a contradiction. So then we can say, well, if 2 angles have the same measure, that has to be false. So they must all have different measures. Here's one for you to try. See if you can prove this one. We're trying to prove that y is not equal to 6. So your assumption will be the opposite of that, and see if you can go ahead and prove this to be false. All right, I hope you gave that a try. Let's take a look at what we would do to prove this to be false. So our assumption will be, we're going to assume that y equals 6, okay? And if y equals 6, then we can go ahead and write 7 times x plus 6 is equal to 70. And if we distribute our 7, we get 7x plus 42 is equal to 70. Now when we subtract 42 from both sides, we get on the right-hand side, let me just get that written out there for you. On the right-hand side, we get 70 minus 42 is equal to 28. And these 42's dropped out, they add to 0, so we have 7x equal to 28. Dividing by 7, we get x equals 4. But if we go back up to our the beginning of the problem, it says x cannot equal 4. That's a given statement. And so we see here that we have a contradiction. So since these two contradict each other, then y must not equal 6. So then we've proven that y cannot equal 6. All right, here's your lesson check. Try these 2 problems and bring your answers to class, and we will talk about those when I see you next time.